Hi, and welcome to this video about the trapezoid rule. Consider the problem of finding the area beneath a curve. By now, you probably should be familiar with the method of using Riemann sums, where we partitioned the domain of the curve into segments of equal width and then draw rectangles up to the height of the curve. The sum of the area of these rectangles gives us an estimate of the area beneath the curve. The more rectangles we use, the more narrow the rectangles become, and the closer our estimation is to the true answer. You should already know about left and right Riemann sums, but today we will discuss a new method, the trapezoid rule, that will give us greater accuracy without having to increase the number of partitions used. Let's begin with an example. Use the left and right Riemann sum methods to generate estimates for the area beneath the curve y equals x squared plus 1 on the domain x from 0 to 3, using a step size or width of s equals 1. Our curve y equals x squared plus 1 looks like this on a graph. Since we are considering the domain x from 0 to 3 with step size or width of 1, we will be paying special attention to the points on the curve where x equals 0, 1, 2, and 3. These points will help us construct 3 rectangles. Now, for the left Riemann sum, the height of each rectangle will be equal to the height of the point of the curve at the leftmost point of that rectangle. The first rectangle, whose left edge lies on x equals 0, will have a height equal to y of 0, which is equal to 0 squared plus 1, which is equal to 1. The second rectangle will have height equal to y of 1, which equals 2. And the third rectangle will have a height equal to y of 2, which equals 5. Again, these rectangles will look like this. Alternatively, the rectangles for the right Riemann sum are constructed so that their heights are equal to the height of the curve at their rightmost point. So then the first rectangle has a height of y of 1, which equals 2. The second has a height of y of 2, which equals 5. And the third has a height of y of 3, which equals 10. These rectangles look like this. Notice that in both the left and right Riemann methods, our rectangles each cover either too much or too little area. The red rectangles representing the left sum leave a significant area unaccounted for, while the blue rectangles, which represent the right sum, count far too much. To get a better approximation for the area beneath our curve, we can narrow the step size and construct more narrower rectangles. However, this can be very time-consuming, and that's where our trapezoid rule comes in. What if, instead of measuring area with rectangles, we connect the dots between steps to form trapezoids? Continuing with our initial function and domain, this is what those trapezoids would look like. What a drastic improvement from the left and right Riemann sums. To show just how major it actually is, note that the left Riemann sum with 3 rectangles estimated that the area beneath our curve was near 8. The right Riemann sum with 3 rectangles estimated that the area was near 17. The true value of the area beneath the curve is equal to 12. And in the same 3 partitions, the trapezoid rule estimated that the area was near 12.5, with an error of only 0.5. Now that we can clearly see how effective the trapezoid rule is, let's discuss how we actually form these trapezoids and how to compute the sum of their areas. For this example, consider the function f of x equals negative 1/4 x squared plus 4x on the domain x from 2 to 10 with 4 trapezoids and step size s equals 2. So we're going to write out all this information so that we don't forget it. So f of x, we said, is equal to negative 1/4 x squared plus 4x. Then we said that our domain is from 2 to 10, so we're going to say that our domain is from 2 to 10, and we're going to write it in interval notation. And then our trapezoids have a step size of s equals 2. So that we have an idea of what we are working with, this is what our function looks like. Since our step size is 2, each trapezoid's base will have a width equal to 2. And we will be drawing our trapezoids between x equals 2, x equals 4, x equals 6, x equals 8, and x equals 10. The first trapezoid will be between x equals 2 and x equals 4, so we need to find the value of the function at those points first. So let's find f of 2. To find f of 2, we plug in a 2 anywhere we see an x, so we have negative 1/4 times 2 squared plus 4 times 2. This is equal to negative 1/4 times 4 plus 4 times 2. Which is equal to negative 1 plus 8, which equals 7. So f of 2 is equal to 7. Now let's find f of 4. So f of 4 is equal to negative 1/4 times 4 squared plus 4 times 4, which is equal to negative 1/4 times 16 plus 4 times 4, which is equal to negative 4 plus 16, which equals 12. So f of 4 equals 12. The top diagonal portion of the trapezoid can be drawn by connecting these 2 points with a straight line. With this information, we now know what our first trapezoid will look like. Remember from geometry that the area of a trapezoid can be found using the formula area is equal to base 1 plus base 2 over 2 times the height, where in this case, base 1 is the length of the left side, base 2 is the length of the right side, and h is the width of the base. In these problems, h is equal to our step size s. When we notice that the lengths of the left and right sides are just equal to the height of the curve at those points, we can rewrite the formula like this, where x sub 0 and x sub 1 are the left and right endpoints of that trapezoid. Now that we've got a formula, we can easily determine the areas of our trapezoids. For the first one, we plug in x sub 0 equals 2 and x sub 1 equals 4 to find its area. So this is going to be the first area that we find, so we're going to call it a sub 1. And that's equal to f of 2 plus f of 4, because remember, these are the bases of our trapezoids, over 2 times the step size, which is 2. So now we plug in our values. F of 2 is 7, f of 4 is 12, over 2, and we said our step size is also 2. So if we multiply, we can see that our 2's cancel out, and we're left with 7 plus 12, which is 19. Before we move on to our second trapezoid, we're going to start a running list over here of all our values. So we have f of 2 is equal to 7, f of 4 is equal to 12, and a sub 1 is equal to 19. This will make it easier for us to reference them later. The second trapezoid starts at x equals 4 and goes to x equals 6, so we can plug those values into our formula. We already know that f of 4 is equal to 12, so we need to calculate f of 6 before we can plug it into our formula for area. So f of 6 is equal to negative 1/4 times 6 squared plus 4 times 6, which is equal to negative 1/4 times 36 plus 4 times 6, which equals negative 9 plus 24, which is equal to 15. So f of 6 is equal to 15. So now we can find our second area. So a sub 2 is equal to f of 4 plus f of 6, because those are the two bases of our trapezoids, over 2 times our step size. So f of 4 is equal to 12, f of 6 is equal to 15, divide by 2, and multiply by the step size of 2. Again, we can cancel out our dividing by 2 and multiplying by 2, and then we're left with 12 plus 15, which is 27. So let's add these two values to our list over here. So f of 6 is equal to 15, and a sub 2 is equal to 27. For the third trapezoid, we need to compute f of 8. So f of 8 is equal to negative 1/4 times 8 squared plus 4 times 8. This equals negative 1/4 times 64 plus 4 times 8, which equals negative 16 plus 32, which equals 16. Now we can find the area of the third trapezoid. So our third area, a sub 3, is equal to f of 6 plus f of 8 over 2 times s. F of 6 is equal to 15 plus f of 8 is equal to 16 over 2 times the step size, which equals 2. Again, our 2's will cancel out, and we're left with 15 plus 16, which is 31. Let's add these values to our list. F of 8 equals 16, and a sub 3 equals 31. We've got one last trapezoid to go, so we need to compute f of 10 to solve for that one. F of 10 is equal to negative 1/4 times 10 squared plus 4 times 10, which is equal to negative 1/4 times 100 plus 4 times 10. This is equal to negative 25 plus 40, which equals 15. So the area of our fourth trapezoid, a sub 4, will be equal to f of 8 plus f of 10 over 2 times our step size. F of 8 equals 16 plus f of 10 equals 15 over 2 times our step size of 2. These 2's cancel each other out, and we're left with 16 plus 15, which equals 31. So let's write these final values to our list over here. F of 10 is equal to 15, and a sub 4 is equal to 31. Our trapezoids for this example look like this. Our estimate of the area beneath the curve from x equals 2 to x equals 10 using 4 partitions is then equal to the sum of these 4 areas. So our total area is equal to a sub 1 plus a sub 2 plus a sub 3 plus a sub 4. So let's look at all these values and add them together. A sub 1 is equal to 19. A sub 2 is equal to 27. A sub 3 is equal to 31. And a sub 4 is equal to 31. If we add all these values together, we'll get a total area of 108. The exact area beneath this curve is equal to 109.3 repeated. So this is a very good estimate. For comparison, the left Riemann sum with 4 rectangles would have given us 100, and the right Riemann sum would have given us 116. Because we compute the values of each trapezoid using the same formula, we can write the following summation as a formula for the entire process. In this formula, the subscripts simply denote which x values are being dealt with, and these change from trapezoid to trapezoid along the way. The leftmost point of the domain is denoted by x sub 0, and the rightmost point is denoted by x sub n, where n is the number of trapezoids. Let's do one more example. Use the trapezoid rule to estimate the area beneath the function f of x equals negative x cubed plus x squared plus x on the domain x equals 0 to x equals 1.5 with a step size of s equals 0.5 and 3 trapezoids. So we have our function f of x is equal to negative x cubed plus x squared plus x. Our domain is from x equals 0 to x equals 1.5. So if we write that in interval notation, that'll look like this. And then our step size is s equals 0.5. To find the areas of each trapezoid, we'll need the values of f of 0, f of 0.5, f of 1, and f of 1.5. So let's go ahead and calculate those now. So f of 0 is equal to negative 0 cubed plus 0 squared plus 0, which is all equal to 0. F of 0.5 is equal to negative 0.5 cubed plus 0.5 squared plus 0.5, which equals negative 0.125 plus 0.25 plus 0.5, which equals 0.625. F of 1 is equal to negative 1 cubed plus 1 squared plus 1, which is equal to negative 1 plus 1 plus 1, which equals 1. And finally, f of 1.5. This is equal to negative 1.5 cubed plus 1.5 squared plus 1.5. So this is equal to negative 3.375 plus 2.25 plus 1.5, which is equal to 0.375. Let's create a list of these values so we can reference them when we start finding the areas of our trapezoids. So f of 0 is equal to 0. F of 0.5 equals 0.625. F of 1 is equal to 1. And f of 1.5 is equal to 0.375. From these calculations, we can tell that the function goes up until it peaks, then starts coming down again, which is reflected in its graph. Now let's start finding the areas of our trapezoids. The area of our first trapezoid, a sub 1, is between the values of x equals 0 and x equals 0.5. So let's plug that into our formula. A sub 1 is equal to f of 0 plus f of 0.5 over 2 times our step size. So this is equal to 0 plus 0.625 over 2 times our step size of 0.5. If we plug these values into a calculator, we'll get 0.15625. Moving right along, let's find the second trapezoid's area. A sub 2 is equal to f of 0.5 plus f of 1 over 2 times our step size. F of 0.5 is 0.625 plus f of 1 is 1 over 2 times our step size of 0.5. Again, we can plug this into our calculator and get 0.40625. And now we can calculate the third and final trapezoid. So a sub 3 is equal to f of 1 plus f of 1.5 over 2 times our step size of s. And f of 1 is equal to 1. F of 1.5 is 0.375 over 2. Here's where we plug in our step size of 0.5. And again, we can plug these into a calculator and get 0.34375. For this example, our trapezoids look like this. To finish our estimation of the area beneath the curve, we simply add all our areas together. So our total area is going to be equal to a sub 1, which is 0.15625, plus a sub 2, which is equal to 0.40625, plus a sub 3, which is equal to 0.34375. And we can plug all this into a calculator to get 0.90625. This solution, like the other examples, is a good estimate. The true value of the area we are estimating is approximately 0.984. It is worth noting that accuracy can be improved for any and all of these methods by decreasing the step size and increasing the number of partitions. But clearly, the trapezoid rule gives us the best accuracy of these methods with the same number of steps. I hope that this video has been helpful in shaping your understanding of the trapezoid rule and how to use it. Thanks for watching and happy studying!